What if gravity suddenly stopped working right now? In an instant, everything around us, your phone, the chair you're sitting on, even the air you breathe, would fly off into space. This invisible force is so fundamental to our existence that we rarely stop to think about it. Yet gravity is one of the greatest mysteries in the universe, shaping everything from the fall of an apple to the motion of galaxies. Today, we're going on a journey through time, from Isaac Newton's groundbreaking ideas to Albert Einstein's revolutionary theory, and even beyond to the frontiers of modern physics. Along the way, you'll discover how our understanding of gravity has evolved, and why scientists still aren't entirely sure how it works. Buckle up, because this story will change the way you see the world. Long before Newton or Einstein, people looked at falling objects and wondered, why do things drop to the ground instead of floating away? Ancient civilizations saw gravity not as a force but as part of the natural order. Aristotle, one of the first to seriously study motion, believed objects fell because they sought their natural place, earth rushing toward earth, fire toward the heavens. His ideas dominated for centuries, but they missed something crucial: why objects of different weights fell at the same speed. Meanwhile, in the medieval Islamic world, thinkers like Al-Hazen challenged these notions. He conducted experiments with light and motion, suggesting that objects moved not because of some mystical pull but through consistent, observable laws, even if he couldn't yet define them. These early attempts may seem strange now, but they were vital stepping stones. Without them, science might never have questioned the unseen forces shaping our world. Imagine standing on the shoulders of those early scholars, peering into the unknown, each flawed theory, every observation adding another piece to the puzzle. Then came Galileo, a man who didn't just ask questions, he rolled up his sleeves and tested them. Picture this: standing at the top of the Leaning Tower of Pisa, he drops two spheres of different weights. The crowd below expects the heavier one to hit the ground first, just as Aristotle claimed, but with a thud they land together. That simple experiment shattered centuries of belief. Galileo didn't stop there. He built inclined planes, gently sloped ramps where he could slow down the motion of falling objects and measure their speed. By marking distances and timing each roll, he discovered something astonishing. Objects accelerate at the same rate, no matter their weight. It wasn't some mystical, natural place pulling them. It was a predictable, mathematical force. This was more than just a discovery. It was the birth of the scientific method itself. Galileo's work laid the foundation for Newton, proving that nature follows laws we can uncover through observation and experiment. Think about that next time you drop your keys. What feels ordinary is actually the echo of a revolution. The legend goes something like this: a young Isaac Newton, sitting under an apple tree in his family's orchard, watched as a fruit broke loose and tumbled straight down. That falling apple, whether it actually struck his head or not, planted a seed of an idea. Why did it fall perpendicular to the ground? Why not sideways or upward? That simple question led to an insight so profound it reshaped science forever. Newton realized that the same force pulling the apple toward the Earth must also govern the Moon's orbit around our planet, and even the planets circling the Sun. In one elegant stroke, he unified the heavens and the Earth. His law of universal gravitation stated that every particle of matter attracts every other with a force proportional to their masses and inversely proportional to the square of the distance between them. That inverse square part is key. Double the distance and the force weakens by a factor of 4. Triple it and the force drops to a ninth. This mathematical precision explained not just falling apples but the elliptical paths of comets, the tides dragged by the Moon, and the delicate balance holding the solar system together. When Newton published his groundbreaking work, Philosophiae Naturalis Principia Mathematica, in 1687, the scientific world was forever changed. Suddenly, the universe wasn't ruled by mysterious impulses, it obeyed equations. Astronomers could predict planetary motion with astonishing accuracy. Engineers could calculate trajectories. The cosmos became a vast, predictable clockwork. Yet even Newton admitted there was something unsettling about his own theory. How could gravity act instantly across empty space with no visible medium connecting the stars? He called it action at a distance, a force he could describe mathematically but never fully explain. That lingering mystery would haunt physics for centuries, waiting for another mind to unlock its deeper secrets. For now, though, Newton's law stood as a towering achievement. It wasn't just about math, it was a new way of seeing the world. Every falling leaf, every thrown ball, every orbiting planet suddenly made sense under the same universal rule. The universe, it turned out, spoke the language of gravity, and Newton had just translated its first words. Newton's ideas didn't just explain gravity, they reshaped humanity's entire relationship with the cosmos. For over 200 years, his laws reigned supreme, turning the universe into what scientists called a clockwork mechanism. Picture an enormous, intricate pocket watch, every gear, every spring moving with perfect precision, governed by unbreakable rules. Planets weren't wandering mystically through the heavens. They were celestial bodies obeying Newton's equations, their paths calculated centuries in advance. Astronomers could predict eclipses down to the second. Navigators charted sea voyages using the moon's gravitational pull on the tides. Even the erratic behavior of comets, once seen as omens, became predictable orbits under Newton's math. This deterministic view wasn't just about astronomy. Engineers harnessed Newton's principles to build bridges that wouldn't collapse under their own weight. Artillery officers adjusted cannon trajectories with newfound accuracy. The Industrial Revolution itself relied on understanding forces and motion. Every steam piston, every spinning gear echoed Newton's laws. The universe, it seemed, was a place of perfect order. If you knew an object's position and velocity at any moment, you could, in theory, trace its entire future path. Yet cracks began to appear in this clockwork vision. Tiny discrepancies in Mercury's orbit stubbornly refused to fit Newton's predictions. Scientists scrambled to explain it, even proposing hidden planets or subtle adjustments to the equations. But the real problem went deeper. Newton's laws worked flawlessly for everyday scales, falling apples, sailing ships, even most planetary motion. But when pushed to extremes near the speed of light or within the warped fabric of space itself, they faltered. Gravity, it turned out, was still hiding secrets. What made Newton's framework so enduring wasn't just its accuracy, but its sheer elegance. With just a few equations, he unlocked the motion of the cosmos. Yet by the dawn of the 20th century, a new revolution was brewing, one that would challenge the very notion of gravity as a force. The clockwork universe was about to get a lot more complicated. Newton's laws worked so brilliantly for so long that when they finally met their limits, even the most devoted scientists had to pause. Take Mercury, the smallest and fastest moving planet in our solar system. For decades, astronomers noticed something odd. Its orbit didn't quite match Newton's predictions. Instead of tracing a perfect, repeating ellipse, Mercury's path slowly precessed, its closest point to the Sun drifting slightly with each orbit. The difference was tiny, just 43 arcseconds per century, but it was undeniable. At first, astronomers scrambled to explain it within Newton's framework. Maybe an undiscovered planet, Vulcan, lurked near the Sun, tugging on Mercury, or perhaps the Sun's faint outer atmosphere created drag. But no matter how they tweaked the numbers, Mercury refused to obey. Meanwhile, another mystery gnawed at the edges of physics. How did gravity actually work? Newton had described its effects with stunning precision, but he'd left the mechanism unexplained. How could one object pull another across millions of miles of empty space instantly, without any visible connection? Newton himself called this idea of action at a distance absurd, yet his equations demanded it. By the late 19th century, new discoveries only deepened the confusion. Light, for example, behaved like a wave, but waves needed a medium like sound through air or ripples through water. Scientists proposed an invisible ether filling space to carry light waves. But if the ether existed, why couldn't gravity use it too? Experiments to detect the ether failed spectacularly, leaving physics in crisis. Then came James Clerk Maxwell's groundbreaking work on electromagnetism, revealing that electric and magnetic fields traveled at the speed of light. Suddenly, Newton's idea of instantaneous gravitational attraction seemed outdated. If electromagnetic forces had speed limits, why wouldn't gravity? The stage was set for a revolution, one that would require not just new equations, but an entirely new way of thinking about space, time, and the very fabric of reality. The universe was whispering its secrets, and a young patent clerk named Albert Einstein was listening. Picture this: you're in a windowless elevator gliding smoothly upward. As it accelerates, you feel your feet press harder against the floor, just like they would if gravity had suddenly grown stronger. Now imagine the opposite. The elevator's cable snaps and you begin free falling. Weightless, untethered, you float inside the cabin as if gravity vanished completely. What Einstein realized in a flash of insight is that these two scenarios aren't just similar, they're fundamentally identical. There's no experiment you could do inside that falling elevator to prove whether you're plummeting toward Earth or drifting in deep space. This was Einstein's happiest thought, the moment he grasped the equivalence principle, the radical idea that gravity and acceleration are two sides of the same coin. It wasn't just a quirky observation, it rewrote physics. Newton had treated gravity as a mysterious force acting across space, but Einstein flipped the script. Maybe gravity wasn't pulling objects at all. Maybe massive bodies like planets and stars were actually bending the very fabric of space and time around them, and objects simply followed the curves of this warped landscape. Think of it like placing a bowling ball on a trampoline. The ball creates a dip in the fabric, and if you roll a marble nearby, it spirals inward, not because of some invisible force, but because the surface itself is curved. Now imagine that trampoline is spacetime and the bowling ball is the sun. Planets orbit not because they're pulled, but because they're rolling along the contours of a cosmic terrain bent by mass. Einstein's elevator thought experiment wasn't just poetic, it was a precision tool. By equating gravity with acceleration, he tied them together with mathematics. If you couldn't tell the difference between standing on Earth and being in a rocket accelerating at 9.8 meters per second squared, then gravity must be more about geometry than force. This leap of intuition took 7 grueling years to formalize into the equations of general relativity, but the seed was planted in that single, joyous realization. The universe, it turned out, was far stranger and far more elegant than anyone had dreamed. Einstein's revelation didn't just tweak Newton's ideas, it tore up the rulebook entirely. Forget invisible forces acting across empty space. Instead, picture the entire universe as a vast, stretchy fabric, a cosmic mesh where time and space are woven together into a single entity, space-time. Every object with mass, from a pebble to a planet, rests on this fabric, creating dips and curves. The heavier the object, the deeper the dent it leaves. Now imagine rolling a marble past a bowling ball sitting on that fabric. The marble doesn't get pulled by some mysterious force, it simply follows the curve created by the bowling ball's weight. That's gravity in Einstein's universe. The Earth orbits the Sun not because it's being magically tugged, but because it's rolling along the Sun's immense space-time dimple like a car circling a roundabout. Even light, which has no mass, bends as it travels through these warped regions. A prediction proven during a solar eclipse when stars appeared slightly out of place, their light curving around the Sun's gravitational well. Newton's action at a distance had been a placeholder, an eerily accurate mathematical trick without a physical explanation. Einstein replaced it with something tangible, spacetime itself, flexing and bending like a trampoline underfoot. Suddenly, gravity wasn't a force at all. It was the shape of the stage on which the universe performed. And just like a wrinkle in a rug changes how a rolling ball moves, warped spacetime dictates the paths of planets, galaxies, and even the flow of time itself. The implications were staggering. If spacetime could bend, then it could also ripple, giving rise to gravitational waves, faint tremors from colliding black holes that took a century to detect. Clocks would tick slower in stronger gravitational fields, a reality GPS satellites now account for daily. Einstein's equations didn't just solve Mercury's orbital quirks, they revealed a cosmos far more dynamic and interconnected than Newton ever imagined. The universe wasn't a clockwork mechanism, it was a living, breathing geometry. Einstein's vision of warped spacetime wasn't just poetic, it was packed with math so intricate even some physicists shuddered. At its heart are the field equations, a set of 10 interwoven formulas that describe how matter and energy sculpt the universe's geometry. Think of them as the universe's own recipe. Toss in stars, planets, or even light, and these equations spit out the exact shape of spacetime around them. The real magic lies in two key ingredients, the stress-energy tensor and the metric tensor. The stress-energy tensor acts like a cosmic inventory, cataloging how much mass, energy, and pressure exist at any point in space. It's the what of the equation, the stuff that tells spacetime how to bend. The metric tensor, on the other hand, is the how, a mathematical blueprint that tracks every curve, twist, and ripple in spacetime's fabric. Together, they form a dynamic dance. Matter dictates geometry, and geometry guides matter's motion. Now, here's the wild part. These equations aren't static, they're alive. A collapsing star, a speeding galaxy, even the expansion of the universe itself constantly rewrites the script. Solving them fully often requires supercomputers, but their elegance is undeniable. Take black holes, cram enough mass into a tiny space, and the equations predict spacetime curving so sharply that not even light can escape. Or gravitational waves, ripples in spacetime itself, confirmed a century after Einstein scribbled them into existence. For all their complexity, the field equations distill a profound truth. The universe isn't just in space and time, it is space and time, a cosmic canvas forever stretching, folding, and rewriting itself. And somewhere in those tangled symbols lies the answer to how it all holds together. The year was 1919, and the scientific world held its breath. On an island off the coast of West Africa and in the rainforests of Brazil, two teams of astronomers braved unpredictable weather, wartime tensions, and temperamental equipment, all for a fleeting glimpse of a cosmic coincidence. The moon would pass directly in front of the sun, plunging the daytime sky into an eerie twilight. But this wasn't just any eclipse. It was humanity's best chance to test a revolutionary idea. Einstein's prediction that starlight grazing the sun would bend, proving spacetime itself was warped. Leading the charge was British astrophysicist Arthur Eddington, a man as passionate about relativity as he was about pacifism in the shadow of World War I. While some dismissed Einstein's theory as German science, Eddington saw its beauty and staked his reputation on validating it. His team on the island of Principe endured torrential rain until, mere minutes before totality, the clouds parted. Through the darkness, they captured images of stars that shouldn't have been visible near the sun's edge, their light deflected by the sun's gravity, appearing slightly out of place. When Eddington announced the results months later, the numbers matched Einstein's equations almost perfectly. The headlines exploded. Lights all askew in the heavens, blared the New York Times. A once obscure theoretical physicist became an overnight sensation. Cartoons depicted the universe as a stretched rubber sheet. Philosophers debated the nature of reality. Even those who didn't grasp the math felt the seismic shift. Newton's absolute space and time were gone, replaced by a dynamic, bendable cosmos. This wasn't just a victory for Einstein. It was a triumph of curiosity over dogma, of international collaboration in a fractured world. That eclipse didn't just illuminate the heavens, it lit the path to modern physics, where black holes, expanding universes, and gravitational waves awaited discovery. And it all hinged on starlight, a tropical storm, and one physicist's refusal to let prejudice cloud the truth. Picture the most extreme victory of gravity imaginable, a place where space-time doesn't just bend but breaks. Black holes aren't cosmic vacuums sucking everything in. They're monstrous pits in the fabric of reality itself. Einstein's equations predicted them, but even he doubted such things could exist. Yet here's the chilling truth. When a massive star collapses under its own weight, it doesn't just shrink, it punches a hole through space-time, creating a gravitational trap so deep not even light can crawl out. At the edge of every black hole lies the event horizon, a point of no return. Cross it, and every path forward in time leads inexorably inward, like a river cascading toward a waterfall with no bottom. But the real terror lies in what happens next. Imagine free falling toward the center. The pull on your feet grows stronger than on your head, stretching you thinner and thinner, a process scientists call spaghettification. Your atoms unravel like cosmic taffy until, well, no one knows for sure. The laws of physics as we know them cease to exist at the singularity, where density becomes infinite and space-time curves into oblivion. Time warps just as dramatically. From an outsider's perspective, you'd appear to freeze at the event horizon, moving slower and slower until you fade from view. But for you, time ticks forward normally, a one-way descent into the darkness. Black holes don't just bend the rules, they rewrite them, revealing gravity's true power when unleashed without limits. These cosmic anomalies aren't just theoretical curiosities, they're proof that the universe still holds mysteries beyond our wildest imagination. For centuries, astronomers relied on light to explore the cosmos, but what if the universe had another way to communicate? Imagine two black holes locked in a final dance, spiraling closer and closer until they collide with a force so immense it jiggles the fabric of reality itself. The shockwaves from that impact don't travel through space, they ripple across space-time, stretching and squeezing everything in their path like a cosmic rubber sheet. These are gravitational waves, and in 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, finally caught one. Picture LIGO as the most sensitive microphone ever built, tuned not to sound but to space-time tremors. Twin detectors, separated by thousands of miles, use lasers bouncing down mile-long vacuum tunnels to measure shifts smaller than a proton. When that fateful signal arrived, a faint chirp, lasting just a fifth of a second, it carried the fingerprint of two black holes merging 1.3 billion years ago. The event released more energy than all the stars in the observable universe combined. Yet by the time the waves reached Earth, they warped LIGO mirrors by less than 1,000th the width of a nucleus. This wasn't just a detection, it was a revolution. For the first time, we could hear the universe uncovering collisions invisible to telescopes. Each wave is like a drumbeat echoing from the darkest corners of reality, revealing black holes we never knew existed, neutron stars tearing each other apart, and perhaps one day the birth cries of the cosmos itself. Einstein predicted these ripples a century ago, but even he thought they'd be too faint to ever catch. Turns out the universe had been whispering all along, we just needed the right ears to listen. Galaxies should be cosmic carousel stars orbiting faster near the center, slower at the edges, just like planets in our solar system. But when scientists measured actual galaxies, they got a shock. Stars on the outer rims were whipping around just as fast as those near the middle. It made no sense under Newton's laws or even Einstein's. Those stars should have been flung into the void unless something invisible was holding them together. That missing ingredient, dark matter, a ghostly substance that outweighs all visible stars and gas by 5 to 1. Unlike black holes or dim stars, it doesn't emit, absorb, or reflect light. We only know it's there because of its gravitational grip on galaxies, like an unseen hand guiding a spinning top. So what could it be? The leading suspects are WIMP, weakly interacting massive particles, hypothetical heavyweights that barely touch ordinary matter, passing through entire planets like a ghost through walls. Then there are actions, ultralight particles so ethereal they could dance on a neutrino's shadow. Labs worldwide hunt for them in abandoned mines and deep underground, shielded from cosmic noise by miles of rock. Some experiments look for rare flashes when dark matter bumps into supercooled crystals. Others track the faintest ripples in magnetic fields. Yet after decades, the mystery deepens. Maybe dark matter isn't one thing but a zoo of exotic particles, or perhaps we've misunderstood gravity itself. Either way, this cosmic detective story reminds us, most of the universe isn't just unknown, it's invisible, quietly shaping everything we see while slipping through our fingers like smoke. Here's something that should shatter your intuition about the universe. Not only is everything expanding, but that expansion is getting faster. Picture throwing a ball in the air, expecting it to slow down, only to watch it rocket away faster and faster. That's precisely what astronomers saw in 1998 when studying distant supernova. These exploding stars act as cosmic lighthouses, their brightness revealing how far away they are. But there was a problem: the dimmer ones were too far. The universe wasn't just growing, it was accelerating, as if some invisible hand were pressing harder on the gas pedal with time. This discovery flipped cosmology on its head. Einstein's equations had once included, then discarded, a cosmological constant to keep the universe static. Now it was back with a vengeance, repurposed as dark energy, a mysterious force pushing space itself apart. Unlike gravity, which pulls things together, dark energy behaves like anti-gravity, an inherent property of empty space that grows stronger as the universe expands. Today, it makes up 68% of everything in existence, dwarfing both ordinary matter and even dark matter. What could dark energy be? Maybe it's vacuum energy, quantum particles popping in and out of existence, fueling expansion. Or perhaps it's a new fundamental field, like an invisible ocean we're only beginning to sense. Some theories suggest our understanding of gravity is incomplete, requiring tweaks on cosmic scales. Whatever the answer, one thing's clear: the fate of the universe hinges on this enigma. Will expansion tear galaxies apart, or could dark energy change its nature over time? For now, the cosmos keeps its most profound secret, an unseen driver steering us toward an unknown destiny. Imagine if the universe had two rulebooks, one for the immense, warped realms of black holes and galaxies, another for the vanishingly tiny world of atoms and particles. That's exactly the crisis physics faces today. Einstein's general relativity paints gravity as the curvature of spacetime, elegant and continuous. Yet quantum mechanics describes reality as a chaotic dance of discrete particles, where even empty space fizzes with unpredictable energy. When these two theories collide, like near a black hole's singularity or at the universe's birth, the math explodes into nonsense. Physicists call this the quantum gravity problem, and solving it might be the ultimate key to understanding reality itself. So how do we bridge this divide? One leading contender is string theory, which suggests that particles aren't dots but tiny, vibrating strings. Different vibrations correspond to different particles, like musical notes on a microscopic guitar. More radically, it proposes extra dimensions curled up so small we've never detected them. If correct, this elegant framework could unify all forces, including gravity, under one mathematical roof. But there's a catch. No experiment has yet confirmed these hidden dimensions or strings, leaving some to wonder if it's profound physics or beautiful fiction. Then there's loop quantum gravity, which takes a wildly different approach. Instead of strings, it imagines spacetime as a network of interconnected loops. Think of a cosmic spiderweb where each thread carries a quantum of area or volume. In this view, even spacetime itself is granular at the tiniest scales, preventing the infinite densities that break relativity's equations. Black holes wouldn't have singularities but rebound like springs, possibly birthing new universes. While less popular than string theory, it offers testable predictions like subtle tweaks to the early universe's echo in the cosmic microwave background. Other bold ideas push the boundaries further. Causal dynamical triangulation suggests spacetime assembles itself from tiny, geometric chunks, like a digital pixelation of reality. Entropic gravity argues gravity isn't fundamental but emerges from deeper thermodynamic principles like heat rising from atomic motion. Each theory has its champions and critics, but all share a common goal: to rewrite the rules so the cosmos makes sense at every scale. The stakes couldn't be higher. Unifying these frameworks wouldn't just satisfy scientific curiosity, it could reveal what happened at the Big Bang, whether time existed before it, or if parallel universes lurk in hidden dimensions. For now, the hunt for quantum gravity remains the grandest puzzle in physics, a testament to how much we still don't understand about the fabric of existence. One thing's certain: whichever path proves right, the answer will change everything. Time might feel like the most constant thing in our lives, ticking forward second by second, never slowing or speeding up. But peel back the curtain of the universe and you'll find it's anything but steady. In Einstein's relativity, time is fluid, stretching and compressing like taffy. A clock on a speeding spaceship runs slower than one on Earth. Near a black hole, time grinds to a crawl compared to the distant cosmos. Gravitational waves don't just ripple space, they warp time itself. Here, time isn't a backdrop, it's an active player in the cosmic drama, bending to the whims of matter and energy. Now, zoom into the quantum realm, and time behaves in a way that would baffle even Einstein. Quantum mechanics treats time as a rigid stage, unchanging, absolute. Particles pop in and out of existence. Superposition lets them exist in multiple states at once, but time, it just sits there, an indifferent referee. Worse yet, some quantum gravity theories suggest time might not even be fundamental, just an illusion emerging from deeper, timeless laws. Imagine a cosmic movie where the frames exist all at once, and what we perceive as now is just a single scene in an eternally fixed reel. This clash isn't just technical, it's philosophical. Relativity paints a universe where past, present, and future are relative, shaped by motion and gravity. Quantum mechanics, on the other hand, seems frozen, with no clear arrow of time at its core. Reconciling these views means answering profound questions. Is time real or just a useful fiction? Why do we remember the past but not the future? Could a theory of quantum gravity erase time entirely or redefine it in ways we can't yet grasp? The stakes are dizzying. Without bridging this gap, we can't fully understand the Big Bang's first moments, where both quantum and gravitational effects ruled. Maybe time is like a river on the surface, but grain by grain beneath a continuous flow built from something far stranger. Until we crack this puzzle, time remains the universe's greatest magic trick, something we all experience, yet no one truly understands. What if gravity isn't a fundamental force at all, but something that emerges from a deeper layer of reality, like temperature arising from the motion of atoms? That's the bold claim of physicist Eric Verland, who argues gravity might not be a force in the traditional sense, but a side effect of entropy, the natural tendency of systems to become more disordered. Picture this: when you drop a cup, it shatters into pieces because entropy favors chaos. But Verland takes this idea further, suggesting that gravity itself could be nature's way of maximizing disorder on a cosmic scale. At the heart of his theory is holography, the mind-bending idea that all the information in a three-dimensional space, like our universe, might actually be encoded on a two-dimensional surface at its boundary. Think of it like a movie projected from the edges of reality. In this view, gravity wouldn't be a force transmitted through space-time, but a statistical effect akin to how heat isn't a thing in itself, but the collective buzz of countless molecules. The pull you feel when you trip and fall, just the universe shuffling its cosmic deck, rearranging information to keep entropy high. This isn't just abstract philosophizing. Verlin's math reproduces both Newton's law of gravitation and Einstein's general relativity without needing gravity as a standalone force. It even offers a potential explanation for dark matter, no invisible particles required. Instead, the extra gravitational tug we observe in galaxies could arise from how entropy and information interact on vast scales. Skeptics argue the theory lacks experimental proof, but if verified, it would upend centuries of thinking. The universe might not run on gravity after all, but on something far more subtle, the hidden rules of information itself. Imagine a future where we don't ask how gravity works, but why it emerges from deeper laws. That's the promise of emergent gravity, a theory that turns our understanding of reality inside out, suggesting the cosmos is less a machine and more a cosmic puzzle, constantly rearranging itself to stay one step ahead of disorder. Here's a fresh take on gravity, one that doesn't involve invisible matter at all. Instead of invoking dark matter to explain why galaxies spin faster than expected, a bold theory suggests we've been missing something fundamental about gravity itself. Modified Newtonian dynamics, or MND, proposes that Newton's laws don't break down, they just bend a little under cosmic extremes. At the heart of MND is a simple tweak. At extremely low accelerations like those found in the sparse outer regions of galaxies, gravity behaves differently than Newton or Einstein predicted. It's as if the universe has a hidden speed bump for gravity, making it slightly stronger where conventional physics says it should fade. Remarkably, this adjustment fits galactic rotation curves with surprising precision, matching observations without a single dark matter particle. Stars on the fringes of galaxies whip around just as fast as MND predicts, no invisible glue required. But the theory isn't flawless. While it shines on galactic scales, it stumbles when faced with larger cosmic puzzles like the way galaxy clusters move or the intricate patterns in the universe's first light, the cosmic microwave background. These phenomena still point to something extra, something missing in MND equations. Critics argue it's a clever patch rather than a true revolution, fine-tuned for specific scenarios but lacking the universal reach of dark matter's shadowy influence. The debate rages on, with each side armed with data. MND supporters see elegance in its simplicity, a universe where gravity's rules flex with circumstance. Its detractors counter that dark matter, for all its mystery, explains more of the cosmic canvas. Yet even if MND isn't the final answer, it challenges us to question the obvious. Sometimes the biggest breakthroughs come not from adding invisible pieces to the puzzle, but from asking whether we've misread the rules all along. What if gravity seems weaker than other forces because it's actually leaking, spilling into dimensions we can't see? This wild idea isn't science fiction. It's a serious attempt to explain why gravity is so bafflingly faint compared to electromagnetism or the nuclear forces. Picture an ant crawling along a thin, taut rope. To the ant, the rope is its entire world, a one-dimensional path. But if a beetle lands on that same rope, the ant might never notice because the beetle exists in a perpendicular dimension the ant can't perceive. Now imagine gravity is like that beetle, spread across hidden directions beyond our three-dimensional awareness, diluting its strength in our observable universe. This is the heart of Kaluza-Klein theory, a century-old idea that dared to add a fourth spatial dimension to Einstein's equations. Theodore Kaluza and Oskar Klein proposed that if gravity could propagate through an unseen, curled-up dimension, smaller than an atom, it might explain electromagnetism as vibrations in that hidden direction. Suddenly, gravity and light weren't separate forces but different faces of the same geometric phenomenon. Though the math was elegant, the theory faded when quantum mechanics took center stage until modern physicists revived it with even bolder twists. Enter brainworld models, where our entire universe might be a three-dimensional brain floating in a higher dimensional bulk. Think of it like a slice of bread suspended in a vast loaf. Ordinary matter and light are trapped on our brain, but gravity, unlike other forces, could seep into the bulk, explaining why it feels so weak. Collisions between brains might even trigger cosmic events like the Big Bang. The most dramatic prediction: tiny, curled-up extra dimensions could alter gravity's behavior at microscopic scales. If these dimensions exist, particle smashers like the Large Hadron Collider might one day spot missing energy, a telltale sign of gravity slipping into hidden realms. Or we might detect deviations in gravity's pull between ultra-precise, sub-millimeter scale experiments. Critics argue these ideas stretch plausibility, but their value lies in forcing us to rethink the obvious. If gravity is the odd force out, maybe the answer isn't in what we see, but in what we've been blind to all along. The universe, after all, has never been content to play by the rules we assign it. The idea of anti-gravity sounds ripped straight from a sci-fi novel: hovering cars, floating cities, entire civilizations freed from Earth's pull. But believe it or not, scientists have wrestled with this concept for nearly a century, walking a razor's edge between groundbreaking physics and fringe speculation. Take Thomas Townsend Brown, an inventor who claimed in the 1920s that high-voltage electricity could counteract gravity. His electrogravitic experiments showed small disks appearing to levitate when charged, a phenomenon he insisted wasn't just electromagnetic lift. Mainstream physicists dismissed it as ion wind effects, but Brown's work still fuels conspiracy theories about secret Pentagon anti-gravity projects. Fast forward to today, and the conversation has shifted from wild claims to serious theoretical frameworks. One tantalizing idea is negative mass, a hypothetical form of matter that would repel rather than attract everything around it. Picture two objects, one with positive mass, one with negative. Push the positive one and it accelerates forward like normal, but push the negative one and it accelerates backward like a cosmic nope to Newton's laws. If such material existed, it could theoretically warp spacetime in reverse, creating anti-gravitational effects. The catch: no one's ever found negative mass in nature, and quantum physics suggests it might be inherently unstable, potentially violating energy conservation or causality. Yet mathematically, Einstein's equations allow for it. Some researchers even speculate that exotic phenomena like wormholes or warp drives would require negative mass to stabilize them. NASA Eagleworks Lab has dabbled in these theories, testing far-out propulsion ideas that flirt with the edges of known physics. Then there's dark energy, the mysterious force accelerating the universe's expansion. In a way, it behaves like a cosmic-scale anti-gravity, stretching spacetime itself. Could harnessing this effect ever be possible? Most physicists say no, it's a property of the vacuum, not a force we can bottle. But the very fact that anti-gravitational effects exist in nature keeps the dream alive. For now, anti-gravity remains a paradox, mathematically tantalizing, experimentally elusive. The line between science fiction and future fact is razor thin, but that's where the most thrilling discoveries often hide, in the questions we haven't yet learned to answer. Hollywood has a love affair with gravity, or rather, bending its rules for spectacle. Take Christopher Nolan's Interstellar, where a spacecraft skims the edge of a black hole named Gargantua. The visuals aren't just stunning, they're shockingly precise. A team of physicists crunched Einstein's equations for a year to render that swirling accretion disk, its light warped by gravitational lensing into a fiery halo. Yet for all its accuracy, the film takes creative leaps, like characters surviving tidal forces that should have spaghettified them instantly. That's the dance of pop science, one step toward realism, another toward drama. Then there's The Expanse, a series obsessed with physics authenticity. Ships don't magically bank like fighter jets in space. They flip and burn, relying on thrust gravity during acceleration. Belters raised in low G grow unnaturally tall, their bodies stretched by a lifetime of weak pull. Even the way coffee sloshes in a cup changes between Earth's gravity and a spinning space station's artificial spin. These details matter. They ground the fiction in something tangible, making the sci-fi feel lived in. But not every blockbuster plays by the rules. Remember Sandra Bullock tumbling through the void in Gravity. The film nails the silence of space but fudges orbital mechanics, stacking debris fields in ways real astronauts would call nonsense. And Star Wars, the Millennium Falcon's inertial dampeners might as well be wizardry. That's the trade-off. Some stories prioritize awe over equations, and that's okay. The best sci-fi strikes a balance, using real science as a springboard, then leaping where imagination demands. What makes Interstellar and The Expanse stand out isn't just their commitment to accuracy, it's how they turn physics into poetry. A black hole isn't just a plot device, it's a character shaping time and fate. A spaceship's engine burn isn't just technical jargon, it's the heartbeat of survival. When pop culture gets gravity right, it doesn't just entertain, it invites us to marvel at the real universe's wonders, no artistic license required. Floating through a spacecraft might look fun in movies, but in reality, zero gravity wreaks havoc on the human body. Muscles wither, bones weaken, and even vision degrades over time. That's why scientists have spent decades chasing a deceptively simple goal: artificial gravity, the most practical solution, good old-fashioned spinning. Picture a giant rotating space station like the iconic wheel from 2001, A Space Odyssey. As it turns, centrifugal force flings objects and people outward against the inner walls, creating the illusion of gravity. The faster the spin, the stronger the pull. NASA early designs envisioned habitats hundreds of meters wide, rotating just a few times per minute to avoid dizziness. Because yes, spinning too fast turns your stomach into a carnival ride. But scaling this up isn't easy. Building a spinning colossus in orbit requires materials strong enough to handle the stress, not to mention the logistics of assembly in space. Even then, the Coriolis effect, where fluid dynamics go haywire in rotating frames, means pouring a cup of coffee could send liquid spiraling sideways. Engineers have toyed with tethering two spacecraft together and spinning them like a bowler, but micrometeorites or a snapped cable could spell disaster. For now, centrifuges remain confined to labs where astronauts train in short bursts to readapt to gravity's tug. Now, for the sci-fi dream, what if we could generate gravity on demand, no spinning required? Theoretically, if we could manipulate spacetime as Einstein's equations allow, we might craft gravitational fields like a dial on a thermostat. Some experiments have flirted with this idea using superconductors and intense magnetic fields, hoping to uncover loopholes in general relativity. Others speculate about exotic matter with negative energy density, stuff that could bend spacetime in ways ordinary matter can't. The catch: we've never observed such materials in nature, and the energy requirements would dwarf anything our civilization can muster. Even wilder, harnessing singularities, a tiny, stable black hole smaller than an atom but weighing as much as a mountain could anchor a spacecraft, providing steady gravity without the spin. But containing it would be like bottling a hurricane. One misstep and your ship vanishes into oblivion. For now, artificial gravity remains a patchwork of brute force engineering and far-off speculation. But whether it's spinning habitats or spacetime tweaks, one thing's certain: if humanity's serious about living among the stars, we'll need to learn how to bring gravity along for the ride. What if time travel wasn't just science fiction, but hidden in the fine print of Einstein's equations? General relativity doesn't just bend space, it twists time, creating loopholes where the future could loop back on itself. These theoretical pathways, called closed time-like curves, aren't mere fantasy. There's serious mathematical possibilities. Picture a cosmic treadmill where, if you follow a precise path around a spinning black hole or through a wormhole, you might end up right back where you started, not just in space but in time. But here's where things get messy. Step into one of these loops and you'd face the infamous grandfather paradox. Go back in time, prevent your grandfather from meeting your grandmother, and suddenly, you'd never exist to make the trip in the first place. Does the universe unravel, or does it enforce some unseen rule to prevent contradictions? Some physicists argue that quantum mechanics might step in, where every possible outcome branches into a new timeline, sidestepping the paradox. Others, like Stephen Hawking, propose the chronology protection conjecture, a cosmic safeguard preventing time loops from forming, as if the universe itself despises a plot hole. Yet the debate rages on. Kip Thorne, the astrophysicist behind Interstellar's time-warping science, showed that closed time-like curves don't outright violate relativity, they just demand exotic matter with negative energy to stabilize them. The catch, such matter might not exist or could be so rare that time loops remain tantalizingly out of reach. Meanwhile, quantum physicists toy with retrocausality, where particles influence events in their own past, teasing a microscopic version of time travel that sidesteps paradoxes entirely. The allure isn't just about hopping decades in a DeLorean. Understanding these curves could unlock deeper truths about causality, quantum gravity, and the universe's fundamental architecture. For now, time loops linger at the edge of theory and fantasy, a reminder that even Einstein's masterpiece might still have secrets left to tell. Imagine a cosmic tapestry where every thread is an entire universe, each with its own unique laws of physics. Some might have gravity so weak that stars never form, while others experience it so intensely that black holes dominate the landscape. This is the multiverse hypothesis, a breathtaking extension of theories like cosmic inflation and string theory, where gravity isn't just a constant in our universe, but a variable in an infinite ensemble of realities. Cosmic inflation suggests that our universe is just one bubble in a frothing sea of spacetime, endlessly budding off new universes with different properties. String theory takes it further, proposing a landscape of possible universes, each shaped by the way tiny, vibrating strings fold and twist through hidden dimensions. In some of these universes, gravity could be a dominant force, crushing matter into dense knots. In others, it might be a mere whisper, allowing galaxies to drift apart like scattered dust. What's truly mind-bending is how these variations could arise. If gravity's strength depends on the geometry of extra dimensions, as string theory hints, then a slight shift in those dimensions could render gravity unrecognizable. Picture a tuning fork that vibrates differently in each universe, changing the pitch of fundamental forces. Somewhere out there, a version of reality might exist where gravity is 100 times stronger, turning planets into crushed marbles. Another might have no gravity at all, leaving matter forever unbound. Even more radical is the idea that gravity could leak between universes in this metacosmos, creating bridges where matter or energy bleed from one reality to another. Wormholes, often imagined as shortcuts within our universe, might instead connect entirely different cosmic domains, each with its own gravitational fingerprint. Of course, this is speculative territory. No telescope can peer beyond the edge of our observable universe, let alone into alternate ones. But if the multiverse is real, gravity's role becomes far stranger than Newton or Einstein ever envisioned. It's not just the architect of our cosmos, but a chameleon, shifting its nature across an endless expanse of possibilities. The force that anchors us to Earth might be, in the grand scheme, just one note in a symphony of universes, each playing by its own rules. While Einstein's theories transformed our understanding of gravity over a century ago, scientists today are still putting them to the test with tools so precise they'd boggle the mind. Take LIGO, the Laser Interferometer Gravitational Wave Observatory, where engineers have built what might be the most sensitive measuring device in human history. Its twin detectors, separated by thousands of miles, can catch ripples in spacetime smaller than 1,000th the width of a proton. When two black holes collide over 1 billion light-years away, the resulting gravitational waves stretch and squeeze LIGO 4-kilometer-long arms by less than the diameter of an atomic nucleus, and this machine still manages to register the signal. But LIGO isn't working alone. Upcoming missions like LISA, the Laser Interferometer Space Antenna, will take the hunt for gravitational waves into orbit. Instead of kilometers-long tunnels on Earth, LISA will use 3 spacecraft flying in perfect formation, spanning millions of kilometers. Freed from Earth's seismic noise, it could detect lower-frequency waves like the mergers of supermassive black holes, events so colossal they shake the cosmos for years. Meanwhile, on an entirely different scale, atomic interferometry experiments are probing gravity's subtlest effects. By cooling atoms to near absolute zero and dropping them in vacuum chambers, scientists can track how gravity tugs on them with astonishing precision. Some labs have even detected the faint gravitational pull between tiny gold spheres just 2 millimeters across. It's like weighing a grain of sand by measuring how it bends the fabric of spacetime around it. These experiments aren't just about confirming Einstein was right, they're searching for the cracks in his equations. Could gravity behave differently at quantum scales? Does it leak into extra dimensions? Each new measurement pushes the boundaries of what we know, peeling back another layer of this cosmic mystery. The quest to understand gravity isn't over, it's entering its most thrilling chapter yet. At the smallest scales imaginable, where particles flicker in and out of existence and atoms behave like waves, gravity seems to vanish into the background. In the quantum realm, the other fundamental forces like electromagnetism and the strong nuclear force reign supreme, their effects clear and measurable. But gravity, it's like a ghost slipping through the cracks. Think about this. A single electron's electric field is trillions of times stronger than its gravitational pull. To detect gravity's whisper in the quantum world, scientists have had to devise experiments so delicate they border on the surreal. Take levitating nanoparticles, for example. Researchers now use laser beams to suspend tiny glass beads just a few hundred atoms wide in midair, isolating them from all other forces. By chilling these beads to near absolute zero, they reduce quantum noise, creating the perfect conditions to measure gravity's faint tug. In one groundbreaking experiment, a team observed the gravitational pull between 2 gold spheres, each smaller than a grain of pollen, separated by mere millimeters. The force was unimaginably weak, equivalent to the weight of a virus, yet unmistakably there. But why is quantum gravity such a stubborn puzzle? The trouble is that general relativity, which describes gravity as the curvature of spacetime, and quantum mechanics, which governs particle behavior, operate on entirely different rulebooks. Relativity paints gravity as smooth and continuous, while the quantum world is jittery and discrete. When you try to mash them together, the math explodes into infinities. Imagine trying to merge a symphony with static. Somehow, the notes just don't harmonize. Some theorists suspect gravity might not even be a fundamental force at this scale. Instead, it could emerge from something deeper, like the way temperature arises from the motion of atoms. Experiments with entangled particles where measuring one instantly affects another. No matter the distance, hint that spacetime itself might be woven from quantum connections. If true, gravity could be less like a force and more like a shadow cast by the true architecture of reality. For now, the hunt continues. From superconducting circuits that mimic black holes to atom interferometers probing spacetime's granularity, each experiment edges us closer to rewriting physics' biggest rulebook. The quantum realm is where gravity hides its secrets, and unlocking them might just reveal the universe's deepest blueprint. Gazing into the future of gravitational physics feels like standing at the edge of a vast, uncharted ocean. We've barely dipped our toes into its mysteries, and yet the next wave of discoveries is already cresting on the horizon. Take the LISA mission slated for launch in the 2030s, a trio of spacecraft dancing in formation across millions of kilometers, hunting for gravitational waves with lasers so precise they could detect a ripple in spacetime from a black hole collision halfway across the cosmos. Unlike Earth-bound detectors like LIGO, LISA will tune into the low-frequency hum of the universe, eavesdropping on mergers between supermassive black holes, events so colossal they've been shaking spacetime since before galaxies even formed. But it's not just about bigger detectors. Picture quantum sensors so advanced they could measure the gravitational pull of a single atom. Labs are already experimenting with levitating microscopic particles in near-perfect vacuums, isolating gravity's faintest whispers from the noise of the quantum world. If these techniques scale up, we might one day map gravity with the same precision we currently reserve for electromagnetism, peering into the quantum fabric of spacetime itself. Then there's the theoretical frontier. Some physicists are betting on entropic gravity, the radical idea that gravity isn't a fundamental force but emerges from the universe's relentless drive toward disorder. Others are probing the holographic principle, which suggests our three-dimensional reality might just be a projection from a two-dimensional surface at the edge of the cosmos. If either idea pans out, it could rewrite physics from the ground up, turning gravity from a force into a cosmic side effect. Now fast forward 50 years. Imagine a world where gravitational wave astronomy is as routine as optical telescopes are today, where we track black hole mergers in real time like weather patterns. Or where quantum gravity experiments finally bridge the gap between Einstein's relativity and the subatomic realm, revealing the universe's deepest blueprint. We might even crack dark energy's code, learning to manipulate spacetime itself. The future of gravity research isn't just about solving puzzles, it's about uncovering new layers of reality we can't yet fathom. And the journey, it's only just beginning. Gravity doesn't just hold us to the ground, it shapes the very way we think about existence itself. For centuries, Newton's clockwork universe made the cosmos feel inevitable, a grand machine where every action set the future in stone. If you knew the position and speed of every particle, you could trace their paths like celestial clockwork. That idea, called determinism, painted reality as a cosmic domino chain where gravity was just another gear in the mechanism. But then came Einstein, revealing that gravity wasn't some outside force, it was the stage, bending and warping under the weight of matter and energy. Suddenly, the universe wasn't a predictable machine. It was a living, shifting landscape where even time itself could stretch and slow. This shift rippled beyond physics into philosophy. If spacetime is malleable, what does that say about free will? Are we just following predetermined curves in the fabric of reality, or do we carve our own path? Some argue Einstein's relativity reintroduced a kind of flexibility where gravity creates possibilities rather than constraints. Black holes, for example, aren't just cosmic vacuum cleaners. They're laboratories where time distorts so severely that cause and effect blur. Near the event horizon, an observer watching you fall in would see your clock freeze while you'd feel time pass normally. Which perspective is real? Gravity forces us to grapple with questions like these, dissolving old certainties about a single, objective reality. Zoom out further, and gravity's role in the cosmos feels almost poetic. Without it, stars would never ignite, planets wouldn't form, and the universe would be a formless soup of scattered particles. It's the invisible architect of structure, the sculptor of galaxies, yet it's also the weakest of nature's forces. That paradox hints at something profound. Gravity's gentleness might be why complexity exists at all. If it were stronger, the universe would collapse too quickly for life to emerge. Too weak and nothing would ever clump together. It's as if the cosmos tuned gravity's dial to the precise setting where beauty and order could unfold. So when we study gravity, we're not just unraveling equations, we're peering into the universe's deepest questions. What is time if it can stretch like taffy? Is space a fixed backdrop or a dynamic participant? And how much of reality is shaped by forces we're only beginning to understand? Gravity doesn't just anchor us to Earth, it ties us to the grandest mysteries of all. We hardly notice gravity's quiet choreography in our daily lives until we trip over a curb or watch a toddler take their first wobbly steps. But this invisible force shapes far more than just falls and stumbles. Take the GPS in your phone, for instance. Those satellite signals pinning your location to within a few feet. They'd be off by kilometers if engineers didn't account for Einstein's relativity. Satellites orbit high enough that gravity weakens slightly, making their onboard clocks tick faster than those on Earth. Without correcting for this, your map app would send you spiraling into the wrong neighborhood within minutes. Then there's biology, where gravity's influence runs deep. Trees don't just grow upward, they actively resist gravity's pull in a dance called gravitropism. Their roots push downward, sensing the subtle tug of Earth's mass, while shoots stretch skyward, defying it. Even something as simple as a houseplant leaning toward a window is gravity's work, a quiet competition between light and the planet's relentless pull. And let's not forget the human body. Our bones and muscles evolved under gravity's constant pressure, which is why astronauts returning from long space missions struggle with weakened skeletons and balance issues. The inner ear's delicate vestibular system, our built-in gyroscope, depends on gravity to tell up from down. When it falters, say, on a swaying boat, we're reduced to seasick stumbling. From the way raindrops fall to the rhythm of ocean tides, gravity is the silent conductor of Earth's symphony. It's the reason pancakes flatten on a griddle, why rivers carve canyons over millennia, and how a simple slip on ice becomes a physics lesson in friction and force. Next time you pour coffee or catch a falling book, remember, you're not just moving through the world, you're dancing with the same force that binds galaxies together. From Newton's apple to Einstein's warped spacetime, our understanding of gravity has stretched the limits of imagination. We began with simple equations describing falling objects and arrived at a universe where black holes twist time itself. Every leap forward answered old questions and unveiled even deeper mysteries. Why does gravity remain the odd force out, refusing to fit neatly into quantum mechanics? What unseen threads of dark matter and dark energy weave through the cosmos? The journey is far from over. Richard Feynman once said, "The more you know, the more amazing the world becomes." And gravity proves it. Every time we think we've grasped its nature, it surprises us, rippling across spacetime as gravitational waves, hiding in extra dimensions or emerging from the chaos of quantum foam. The force that pins us to the ground also connects us to the grandest puzzles of existence. So stay curious, look up at the stars and wonder about the invisible hand shaping their path. Drop a ball and marvel at the centuries of insight hidden in that simple fall. And share your thoughts. What gravity fact blows your mind? Is it the way time slows near a black hole, or how the universe might be tuned just right for life? The conversation doesn't end here. The cosmos is still whispering its secrets, and the next chapter is yours to explore.